Alright, this time around we will use the example 4 to design the PID controller. So the design procedure is similar to the PD controller that I have explained in previous video. So the first one is to select model. So let's say we try to be consistent, so we use the ITAE models. Okay, to achieve a 5% overshoot. Again, we will select the zeta to be 0.707, and to achieve TP less than 3 seconds, we select the omega d equals to 1.05. But since we use the third order system, we double the value to be 2 radian per second. So from the value of omega d and value of zeta that we have find, we can calculate the omega n. So the omega n in this case is 2.8, similar to the previous examples. And then since we have the third order system for the ITAE models, we refer to the table of ITAE models. We have this characteristic equation, S plus 0.7, S plus 0.5 plus minus J 1.07. And then we substitute the omega n equals to 2.8 into the characteristic equation because the characteristic equation is based on 1 radian per second. So we need to normalize it to 2.8 radian per second by substitute S to S over 2.8, and then when we put it into the characteristic equation, we will get S plus 2, S plus 1.5 plus minus J3. And then for the PID controller, we have the form of Kc, S plus Zi, S plus Zd over S. So the Zi here indicates that this is the 0 for the PI controller, and Zd here is actually the 0 for the PD controller, because the PID controller is actually the combination of PI and PD controller. So let's say we want to design the PI controller so that the PI controller will cancel the plant pole at S equals to negative 0.3. So we select Zi equal 0.3. Okay, and we want the root locus. We want the point at the root locus to be at this point, negative 1.5 plus minus J3, because we want the overshoot to be 5%, as we have previously mentioned in the first steps of this PID controller design. So what we do here, as the previous examples, we find the Z plus D here. Yeah, we find the Z plus D. What we left here is only S plus 3 and S plus 1, because we have cancelled out. Remember the PI controller. So we have the Kc S plus 0.3, S plus Zd over S, and this is a GC, and we multiply with the plant. The plant is 0.7, S plus 0.3, S plus 1, and we have S plus 3 here. So since we have selected the PI Zi is 0.3, we can cancel for this term. So what's left for the plant is only S plus 1 and S plus 3. And then for the controller, we only have Zd that we want to find. Okay, now the next step is we calculate the angle of S plus Zd here. So using the same method that I have explained, we can find the angle to be 99.5 degrees. Okay, and then using the arctan, you can find the ZD to be 1. Okay, and when you input into the controller, what we have now is actually KC S plus 0.3 S plus 1 over S. So we can put this controller into the CISO tool, and we can try to get where is the location of KC that will yield a 10% overshoot. So we have as 0.3 for the ZI, and then we have another real 0 of ZD, which is located at 1. Okay, so when you input it into the system, and then you can find the location here. So I want to delete this difference. Let's say we delete this design requirement. Okay. Let's try to plot a new where is it? Okay. No, where is the root locus? Yeah, here, the root locus editor. Alright, this one. Alright, so let's say we try to use 5. What will happen is here still not yield 10%. 9. Oh, sorry, this is actually we need to put an integrator. So the PID have an integrator. So I forgot to put the integrator here. So what we have, wow, alright. So where is the rate of 10% overshoot? 10% overshoot is about at this location. Okay, so we have 9.62. At this point, which is the percent overshoot is less than 10%, and TP we have is 1.57, which is less than 3 seconds, and the final value here is 1, which is we have 0 steady state error. So using PID controller, we can get all the design requirements met. Okay, that's good. And then we can calculate the PID parameters using the here you have to compare with the standard term Kp or plus Ki over S plus Kds, which you can get here if you compare together to the controller that we found. We calculated Kd is equals to 9, Ki equals to 2.7, and Kp equals to 11.9. 7, which if you use the MATLAB, you can find actually using PID STD. So let's say we import first, we export the C here, so we export C, and yes, so we try to see what is the C value. So the C value here is actually what is the C value? Oh, here 9 s plus 0.3 s plus 1 over s. So we can use PID of C to get the KP, KD, and KI. Okay, or you can use PID STD of C to get the standard form of KP, TI, and TD. Okay. I think that's it for the PID controller example 4. Okay, so you can try by yourself to get the suitable controller. Okay, thank you very much for your attention. See you again in the next video.